In this lesson, we discuss the integration by substitution. We'll proceed as follows. First, we'll talk about its theoretical background as briefly as possible, and then let us go over to its step-by-step process. And then we're going to do some applications. That is, we're going to solve some problems, mostly on indefinite integrals. And then, of course, we'll do some definite integrals as well. After all those are done, we're going to come back to the theoretical background and then talk a little bit more about some advanced aspects of integration by substitution. Here we go. Integration by substitution is basically a reversed chain rule. Well, what's a chain rule? Well, here it is. We have three aspects of chain rule, remember? Outside in, to take the derivative of outside. Number two, inside stays the same, red part. And then the derivative of the inside, you have to multiply all the way outside, which is emphasized in blue. That's the essence of chain rule. And then this integration by substitution is practical way to do a reversed chain rule. Well, it is briefly explained over here, but it's a little bit meaningless at this moment without an example. So let's go over to example right away. Here is some example. Here are some examples. Look at the first one, 3.1a. We have a composite function here. 16 plus x squared is inside this radical. And you cannot simplify this radical anymore, so we have to do something. And typically what we are going to do is you're going to substitute 16 plus x squared by another character and go from there. And main idea is of course a chain rule. And substitution technique is there to help us out. Some other examples, another chain rule here. We have parentheses. That's going to substitute it into something. How about part C? Denominator is very good example of inside of a composite function because it's a reciprocal function. Here's another typical example. Inside this radical, we have something. So here's a composite example, composite function. So we're going to take this as another character, substitute it, go from there. This is a little bit weird. It doesn't look like a composite function, but believe it or not, substitution can be used for these kind of functions as well. And there are some non-standard examples, and even harder non-standard examples there. Before starting any of those, let's talk about a step-by-step process. Goes like this. Step 0 is usually recognition. We'll talk about it later. Step 1, we take y as inside of the composite function. And then we take the derivative and then calculate the differential. Express dx as, well, dy. What do you mean by these? Let's go over to an example and talk about it. Here it is. Let's look at the first example. We take y as the inside of the composite function. Go ahead with the derivative. It's easy computation. dy dx is 2x. It's easy. And step 3 says expressed dx. So for dx, and it is 1 over 2x times dy. And all of these are going to be necessary calculating this integral. Why? This y equal to 16x squared, 16 plus x squared, is going to be used to simplify this part. 16 plus x squared will be replaced by y. And then this dx part, that will be replaced by 1 over 2x times dy. More specifically speaking, let's go back to the step-by-step process. Well, we talked about step 1, 2, 3. Let's go to step 4. Inside is now y, dx is now, well, that's how we solved it, 1 over something times dy. And then if we put everything, we're going to end up with a y integral. Here it is. 16 plus x squared is now substituted to y. dx is substituted by 1 over 2x times dy. Do you see some cancellation going on? Well, this x and that x cancelled out, and then what do we have? We have a y integral. No x left behind, just purely y. And compared with the previous integral, this is much easier integral. Just a power function. This fifth root of y is nothing more than y to the 1/5 power. So this is y to the 1/5 power. So power rule applies, increase 1 to the power and the reciprocal. And here we go. This is correct antiderivative. However, you cannot stop here, because even though this is correct antiderivative, the original problem was written in terms of x, not by y. So third substitution, y is again equal to 16 plus x squared. Replace that. And then we have the final answer. Of course, I'll leave it as an exercise whether the derivative of this really is equal to that. You can do that by brute force computation. Of course, it'll require chain rule. This kind of thing is called integration by substitution. Substitution number 1, this one red, and then we have a couple of straightforward computation. Derivative, and then solve for dx. And then we have substitution number 2. In the original integration, y substitutes the inside of a composite function. And then this computation in blue, substitute dx. The resulting integral here should simplify itself into a y integral. If it doesn't, either something is really wrong or there's an extra step that you'll have to take. Resulting integral is much simpler than before. If it is worse than before, of course you'll have to find some alternative method. After all, the purpose of all this technique is to make it simpler than before. Calculate the integral and then the final substitution. Let's do this several more times. Let's see, this is a little bit easier. Let's leave it as is. Let's go to problem C. What is the natural candidate of substitution? It's gonna be the denominator. If you have addition or subtraction in the denominator, you cannot separate it. We're stuck with that. So the substitution is a good technique to handle it. So, well, we've been doing y substitution. The character is y, so let's introduce another character. U, okay. U is equal to the denominator, y squared plus 2y. Good. And then we just move on to the next step and then the next step. Straightforward application of the derivative formula. dy over dx is 2y plus 2. Consequently, dy is 1 over 2y plus 2 times du. Just an algebra. But these three are going to be substituted into the original integral and generate much simpler integral. Let's see. So y squared plus 2y, which I highlighted in red, will become just u. And this dy will become, as we calculated, 1 over 2y plus 2 times du, which I highlighted in blue. Now, do we see some cancellation? Well, I hope everybody does. 2y plus 2 is, after all, twice of y plus 1. So they cancel out. I have 2 in denominator, so we end up with 1 over 2 u. What kind of integral is this? 1 over 2 u. Well, u to the negative first power, isn't it? Basically. But negative first power cannot be done by power rule, because if you add 1 to that negative 1 power, you get 0, and you cannot take 0 as a denominator. So you'll see that this is a logarithmic function, and this becomes 1/2 log of u. In order to make the logarithmic function always valid, we take absolute value here to make the inside of the logarithm always positive. Now, this is correct antiderivative, no question about that. But it's not the final form because the original function was written in terms of y. So let's take the third substitution. U equals 2 y squared plus 2y. So let's take the third substitution, and that'll conclude the problem. Okay, so do they look good? Well, alright. Let's review this technique once more, hopefully even once more. Let's go over to the next problem here. This time, let's use trigonometric functions. Do you see a composite function here? Well, I hope you do. Obvious choice. In my opinion, it is obvious at least. The inside of this radical 2 plus cosine of x. Why not the denominator? Why not if you take u as or y as square root of this thing? Well, if you take the derivative, you will see. So you'll get something really complicated. And that's a bell ringer. After all, the purpose of this integration by substitution is to make this integral simpler than before. If you get something worse than before, something is terribly wrong. Alright, here we go. We take y as the inside, 2 plus cosine of x, and then just go right ahead with straightforward computation. Derivative of 2 plus cosine of x is negative sine of x. Consequently, dx is dy over negative sine of x. Equivalently, you can write it as 1 over negative sine of x times dy, if you will. Now that first three steps are done, let's go with integral computation here. Second substitution. Y will be substituted in place of this inside of the composite function, inside of the radical. And then dy over negative sine of x, we calculate it, will be substituted in place of dx. Now, is there a simplification? Well, sine of x cancel out, and then I get integral of y to the negative 1/2 power, because 1 over square root of y is the same as y to the negative 1/2 power. So we can use the power rule as before. Add the power by 1 and then reciprocal. This is correct antiderivative, but not the final form. So subtracting y equals to 2 plus cosine of x, back in, we have the final answer. Okay, let's do just one more example. Let's consider this example, tangent function. This does not look like a composite function, but why did it appear in this section? Well, here we go. Please recall the trigonometric formula. Tangent is sine over cosine. So if you write it like this, then you'll see that denominator is the inside of the composite function. So taking y, u, okay, I decided to use u this time, u as cosine of t. The derivative du over dt is negative sine of t, so dt is du over negative sine of t. Just step 2 and 3 are just straightforward. So if I plug everything in there, then we're going to end up with second substitution here. Tangent is the same as sine of a cosine, and as highlighted, cosine is the inside function, so that becomes u. And as highlighted, dt is du over negative sine of t, and then as before we have cancellation. 1 over negative u, so antiderivative is logarithmic function, and we have negative log of u, and equivalent in negative log of cosine of t. Some manipulation gives you log of secant